Hi students and friends, this is your host and teacher Sayyid Ayazuddin Haider. You're watching Learn and Teach by Sarayaz. So I'm continuing my O-level past papers session and I have IGCSE Chemistry 0620. It's of May-June 2024. The variant is 62. I'm not going to waste my time in reading the other formalities. You know that's paper 6. It's of 1 hour. You have to answer all the questions. Total mark for this paper is 40. Important thing is that you have notes for use in qualitative analysis in the question paper. It's like that. These are the notes for use in qualitative analysis. This includes tests for anions, cations, flame test, as well as tests for gases. So let's start the paper. Question number 1. When a mixture of calcium hydroxide and ammonium chloride is heated, ammonia gas is made. Calcium hydroxide plus ammonium chloride gives calcium chloride plus water plus ammonia. Ammonia gas is soluble in water and toxic. Ammonia gas reacts with hot copper 2 oxide to make nitrogen. Ammonia plus copper 2 oxide gives copper plus water plus nitrogen. A student makes nitrogen using the apparatus shown in figure 1.1. Here's figure 1.1. You can see we have apparatus A, B, we have a chemical substance X. A. Name the items of apparatus labeled A and B in figure 1.1. In A, it's a boiling or test tube. You can see the shape. You can easily identify it's a test tube or boiling tube. B. B is a measuring cylinder. If you see the shape, it's a of measuring cylinder. It's inverted. Into next part, which is part B, the apparatus needs to be heated in two places. On figure 1.1, draw arrows in two places to show where the apparatus should be heated during the experiment. Now it should be heated at this point. That is a reaction between calcium hydroxide and ammonium chloride. So I am going to show the arrow here. 3 arrows will be enough for heating. And it should be heated at this point also, because copper 2 oxide is also heated with ammonia gas coming from ammonium chloride and calcium hydroxide. So this will be the final arrow. Moving to next part, part C. During the reaction, a colorless liquid collects at the point marked X in figure 1.1. Suggest the identity of the colorless liquid. So here we are getting colorless liquid. This is colorless liquid. It's coming from the reaction between calcium hydroxide and ammonium chloride. If you go back and look at the reaction, here's the reaction, calcium hydroxide plus ammonium chloride. We are getting what? We are getting calcium chloride plus water plus ammonia. Calcium chloride exists in the solid state. Ammonia is gas, water is a liquid. So X must be water. So you will write water here. You can even write the formula because they didn't ask you to write the name. Moving to next part, which is part D. Some of the ammonia gas passes over the copper 2 oxide without reacting. Suggest why none of this ammonia gas is collected in the item of apparatus labeled B in figure 1.1. So they are saying some of these are not collected. Definitely, it's also soluble in water, so it will dissolve in water. So you will write dissolves in water. Ammonia is soluble in water. E, the student does not collect the first few bubbles of gas. Suggest why the first few bubbles of gas are not collected. Definitely, first few bubbles are of air. So, right, it is air. F, explain why this experiment should be carried out in a fume cupboard. If you look at the details of the experiment, you see they have already mentioned that ammonia gas is toxic. That's why needs to be carried out in fume cupboard. So you write ammonia is toxic. Moving to question number 2. Question number 2. A student investigates the reaction between aqueous aluminum chloride and two aqueous solutions of sodium hydroxide, solution F and solution G. Solution F and solution G have different concentrations. The student does 3 experiments. So there are 3 experiments in this. Experiment 1, rinse the burette with distilled water and then with aqueous aluminum chloride. Rinse a conical flask with distilled water. Fill the burette with aqueous aluminum chloride. Run some of the aqueous aluminum chloride out of the burette so that the level of the aqueous aluminum chloride is on the burette scale. Record the initial burette reading. Use a measuring cylinder to pour 25 centimeter cube of solution F into the conical flask. Stand the conical flask on a black or dark colored sheet of paper. Slowly add aqueous aluminum chloride from burette to the conical flask while swirling the flask until the mixture in the conical flask just starts to become cloudy. Record the final burette reading. Experiment 2. Refill the burette with aqueous aluminum chloride. Run some of the aqueous aluminum chloride out of the burette so that the level of the aqueous aluminum chloride is on the burette scale. Record the initial burette reading. Rinse the conical flask with distilled water. Rinse the measuring cylinder with distilled water and then with solution G. Use the measuring cylinder to pour 25 centimeter cube of solution G into the conical flask. Stand the conical flask on a black or dark colored sheet of paper. Slowly add aqueous aluminum chloride from the burette to the conical flask while swirling the flask until the mixture in the conical flask just starts to become cloudy. Record the final burette reading. Experiment 3. Refill the burette with aqueous aluminum chloride. Run some of the aqueous aluminum chloride out of the burette so that the level of the aqueous aluminum chloride is on the burette scale. Record the initial burette reading. Rinse the conical flask with distilled water. Use a measuring cylinder to pour 25 centimeter cube of solution G into the conical flask. Add 5 drops of thermophthalein indicated to the conical flask. Stand the conical flask on a white tile. Slowly add aqueous aluminum chloride from the burette to the conical flask while swirling the flask until the thermophthalein indicator changes color. Record the final burette reading. Part A. Use the burette diagrams in figure 2.1, figure 2.2, and figure 2.3 to record the readings for experiments 1, 2, and 3 in table 2.1 and complete table 2.1. So here we are having readings. We need to fill these readings in this table 2.1. So for experiment 1, initial reading will be 1.123. It's 1.3. What about the final reading? It's 14.567. So I will write 14.7. Experiment 2. Initial reading will be 2.567. Final reading will be 2.12345. Experiment 3. Initial reading 0.1234. 0.4 will be the initial reading. Final reading will be exactly 28. Now I am writing down these readings here. That is in table 2.1. So for experiment 1, final reading is 14.7 and initial reading is 1.3. For experiment 2, final reading is 29.5 and initial reading is 2.7. For experiment 3, the final reading is 28 and initial reading is 0.4. Now, in each case, I need to calculate the volume of aqueous aluminum chloride added in centimeter cube. So the first one, 14.7 minus 1.3, 13.4. Experiment 2, 29.5 minus 2.7, we will get 26.8. Experiment 3, 28 minus 0.4, that is 27.6. Moving to next part, which is part B. In experiment 3, the aqueous sodium hydroxide in the conical flask is alkaline. At the end point, the mixture in the flask is no longer alkaline. State the color change seen at the end point in experiment 3. So in experiment 3, here is experiment 3, here is experiment 3. You have added thermophthalein indicator and you are adding aqueous aluminum chloride to the flask containing sodium hydroxide. And you will add until the color changes. So initially the color must be in alkali, that is sodium hydroxide, it's blue, and it's neutral, it becomes colorless. So we'll write blue to colorless. C. State why the conical flask is filled as solution F is added in experiment 1. Definitely we are reacting or mixing reactants. Mixing the contents of the reaction mixture. Part D. Suggest why the conical flask is placed on black or dark colored paper in experiments 1 and 2. So it's easier to observe or see white PPT or cloudiness because these are dark colored. So we must be having something appearing as in the form of white PPT or cloudiness. So you're right, it is easier to observe white precipitates. You can even write or cloudiness. Moving to next part, which is part E1. Explain why the measuring cylinder is rinsed between experiment 1 and experiment 2. Between experiment 1 and 2, why we need to rinse? So in experiment 1, we have used solution F. In experiment 2, we are using solution G. Both are different. So we need to remove this. Remove solution F before proceeding or using the conical flask. So you write Remove solution F. Part 2. Explain why the measuring cylinder does not need rinsing between experiment 2 and experiment 3. So in both experiments, they're using same solution of NaOH used. Same solution of NaOH used for G in both experiments. F. Compare the concentration of solution F used in experiment 1 with the concentration of solution G in experiment 2. Explain your answer. Now, here they are asking uh, the comparison in the concentration of solution F used in experiment 1 with the concentration of solution G used in experiment 2. You have to mention quantitative relationship for the volume used in experiment 1 and 2. Mention quantitative relationship for the volume used in experiment 1 and experiment 2. So let's go to experiment 1 and 2. Here's experiment 1 and 2. See the relationship 13.4 and 26.8. You see in experiment 2, the volume used is high, which means we have a solution G more concentrated. Solution G is more concentrated because large volume of AlCl3 required in experiment 2. So you'll write solution G is more concentrated because larger volume of AlCl3 required in experiment 2. Now in solution in experiment 1, is experiment 1. You see solution F is twice as concentrated than in experiment 2. Now this time they're comparing solution G and F. G and F. Here we are having F and here we are having solution G. So you write the next statement. In experiment 1, solution F is twice as concentrated, than in experiment 2. We are talking about solution G here. If you see here, see the volume used 13.4. It is almost half of 26.8, which means here F is 2 times concentrated. Than this one. Moving to next part, which is part G. Calculate the volume of aqueous aluminum chloride required when experiment 1 is carried out with 10 centimeter cube of aqueous sodium hydroxide instead 25 centimeter cube. So experiment 1, the volume used is 13.4, which is for 25 centimeter cube. So I will write, I'm showing the calculation here, 25 centimeter cube required 13.4 centimeter cube. Therefore, 10 centimeter cube required X. So I will write here like this, X is equal to 13.4 multiplied by 10 divided by 25, which is 5.36 centimeter cube. This will be the volume required if it's carried out with 10 centimeter cube of aqueous sodium hydroxide instead of 25 centimeter cube. H. In all 3 experiments, it's more accurate to measure the volume of the aqueous sodium hydroxide using a volumetric pipette instead of a measuring cylinder. Explain why it's not possible to use a volumetric pipette to measure the volume of aqueous aluminum chloride in these experiments. So definitely volume used is not fixed, or it's not same in each experiment. Volume used is not same in each experiment. Moving to next question, which is question number 3. The student tests 2 substances, solid H and solid H and solution I. Test on solid H. Solid H is barium carbonate. Now they have mentioned the name of the compound which is in solid H. It's barium carbonate. Complete the expected observations. A1. The student adds an excess of dilute nitric acid to the sample of solid H in a boiling tube and test any gas produced. So observations with dilute nitric acid. So nitric acid, it will react with the carbonate. So you write nitric acid plus barium carbonate. The products must be barium nitrate plus water plus carbon dioxide. So carbon dioxide exists in the gas state. It must be the gas produced here. So what's the observation for this gas? It will turn lime water milky when gas is passed through this. So for the observation, what you're going to write, you can write any one observation. It's any one observation for the identity of the gas, and that is it fizzes. There's a fizzing of bubbles. Bubbles. Any one. Bubbles or solid disappears. Now for the observations for the gas, it's turning lime water milky when gas is passed through it. Lime water turns milky when gas is passed through it. Passed through it. The solution produced in A1 is solution J. The student divides solution J into 4 approximately equal portions. B. The student carries out a flame test on the first portion of solution J. Observations. So we are having barium here. So straight away look at the color of barium. The flame test, here's barium. Here's barium. It's giving light green. So you'll write light green flame. Sorry, I didn't write the identity of the gas made here. The identity of the gas is carbon dioxide. It's CO2 or carbon dioxide. And for these observations will be written there, not here, in part 1. So I'll write bubbles or solid disappears. And identity of the gas is carbon dioxide. C. To the second portion of solution J, the student adds a few drops of acidified aqueous potassium magnate 7. And they are talking about the observations. They are adding acidified aqueous potassium magnate 7, which is used for the presence of sulfite or sulfur dioxide gas. We are not getting any sulfur dioxide gas or sulfite ion here. Here is sulfite ion. So you will write the observation, solution becomes pink or pale purple due to the color of potassium magnate 7. Solution becomes pink or pale purple. Moving to next part, which is part D. To the third portion of solution J, the student adds a few drops of dilute sulfuric acid. Observations. So you see here, it's containing barium carbonate. So barium carbonate will react with sulfuric acid, producing barium sulfate plus barium carbonate. You will get what? You will get barium sulfate. Barium sulfate, water plus carbon dioxide. And barium sulfate, we are getting barium sulfate. It's white in color. We have white PPT of barium sulfate. So I will write white PPT here. It's due to the formation of barium sulfate. So these will be the observation for this one. Part E. To the fourth part of solution J, the student adds about 1 centimeter depth of dilute nitric acid followed by a few drops of aqueous barium nitrate. Now the fourth portion, they are adding barium nitrate followed by nitric acid. So there will be no change because barium nitrates used for the presence of the sulfate ion. They are not having any sulfate ion. If you look at the test for the sulfate ion, here's the test for the sulfate ion. The test for sulfate ion is done by adding dilute nitric acid followed by barium nitrate used to test SO4 minus 2 ions. So we will write No change here. Test on solution I. Table 3.1 shows the test and solutions, students' observations for solution I. The student divides solution I into two portions. Test 1. To the first portion of solution I, in a boiling tube, add 2 centimeter cube of aqueous sodium hydroxide and warm the mixture. Test any gas produced using damp red litmus paper. Observations. Damp red means litmus paper turning blue. Okay, this sodium hydroxide is used to identify the presence of positive ions. So if you look at the cations list, positive ion or cation, so ammonium ion, it's producing ammonia gas on reaction with aqueous sodium hydroxide of the sample. So this change, an ammonia gas, the test of the ammonia gas is here. You can see the test of the ammonia gas, turning damp red with litmus paper blue. So it's due to the presence of NH4 positive ion. So it must be having NH4 positive ion. Gas is ammonia. Test 2. To the second portion of solution I in a boiling tube, add 1 centimeter cube of dilute nitric acid followed by few drops of aqueous silver nitrate. A white precipitate form. Now, this test is for the halide ions. Look at the test for the halide ions. Here we are having halide ions. These are the 3 halide ions. Same test, dilute nitric acid, aqueous silver nitrate on all these 3. And in case of chloride ion, we are getting white PPT. So it must be due to the presence of Cl negative ion. F1, identify the gas produced in test 1. It must be ammonia gas. I've already mentioned. So you can either write ammonia or NH3. Number 2, state what is observed when the gas produced in test 1 is tested using damp blue litmus paper. Stays blue or no change. Because it's alkaline, it will only turn red to blue, no effect on blue litmus paper or solution. So write stays blue or no change. G, identify solution I. Solution I must be having ammonium ion, chloride ion. So I will write ammonium. You can even write NH4 positive, chloride ion. Or Cl minus. Moving to last question, which is question number 4. Bismuth is a metal that has a reactivity similar to that of copper. The ore bismuth contains the compound bismuth 3 oxide Bi2O3. Bismuth 3 oxide is insoluble in water and reacts with dilute acids to form an aqueous solution of a salt. The ore bismuth contains no other compounds that are insoluble in water and no other compounds that react with acids to form aqueous solutions. Describe how you could obtain a sample of bismuth metal starting with a large lump of the ore bismuth. You have access to common laboratory apparatus and chemicals. Now, they are not asking you to draw that diagram, anything like that. The total mark for this question is 6. So how you are going to divide? So you have the ore here. So for the first 3 marks, you have to write these steps. You have to crush the ore or make it into small pieces. Then you have to name the apparatus used here. Then you will add water and filter. So for first 3 marks, I will start crush the ore into smaller pieces using mortar and pestle. Second point, add water, then filter. What about other 3 marks? For other 3 marks, you have 3 methods. Any one method. You can either go for the displacement method, number 2, or electrolysis. Now, if you are going for displacement method, you have 2 situations. You will either continue in the solid state or aqueous solution. So if I'll write in A, in solid state, so the steps in the solid state, you have to add more reactive metals. Add more reactive metals like you can even call them reducing agents because they are going to reduce it, or reducing agents because they are reducing the bismuth from the compound to the residue. Here the insoluble part is the one which contains a compound of bismuth. So now you have to write the name of the reducing agents. Name reducing agent. We don't have highly reactive metals in the reducing agent, so no need to write or consider the metals from there. Name reducing agents like you can use carbon or iron or zinc or aluminium or magnesium or hydrogen or even carbon monoxide, CO. Then you will heat to get bismuth. The next scenario is that when you are using going for the aqueous solution. In aqueous solution, now in aqueous solution, you can use named strong acid or salt or more reactive metal. Add named strong acid or more reactive metal. Remember, more reactive metal, not highly reactive metal. So you have to mention not sodium, potassium, or calcium. like zinc, iron, magnesium, or aluminium. So bismuth displaced or reduced from its oxide, which is a compound. Next method, if you'll go for electrolysis method, now I'm going to talk about electrolysis method. You have to add suitably named acid to residue. To residue. Next step, electrolysis of the solution. Go for the electrolysis of the solution. Electrolysis of solution. Name electrodes used here. Name electrodes used, which is either carbon or platinum. Both of these are inert. Last but not least, bismuth produced at cathode. So you can go for one of these in order to get bismuth from its ore. Thanks for watching. Press like and share my videos. For more videos, subscribe to my channel and press the bell icon.